is gases. So the last part we are on gases. So a sample of nitrogen gas occupies this at 100 degrees Celsius at the temperature in degrees Celsius. At what temperature in degrees Celsius would it occupy 234 if the pressure does not change? So if the pressure does not change, we are looking at Charles' law. So let's answer the question. Let's just move this question a bit. So moving this question. So here what we have is Charles' law. According to Charles' law, the volume is directly proportional to the temperature. Therefore, the formula for Charles' law, if you take the T here, you're going to have the V, or should I say, if you introduce now the equal sign, you have your V is equal to T. So KT over T over T. So that's why our Charles' law, we have the Charles' law is equal to volume number 1 over the temperature number 1 should be equal to volume number 2 over the temperature number 2. So the volume number 1 in this case is equivalent to this. So we are told at what temperature in degrees Celsius would it occupy 234. So if the volumes are in the same units, you can use them like that. It will give you the same correct answer. So now what we are going to have is that let's convert this temperature to Kelvin. So the temperature, according to Charles' law, it always has to be in the absolute temperature, which is in kelvins. So the temperature in kelvins should be equal to temperature in degrees Celsius plus our 273.15 degrees, 0.15 degrees. This is going to give us a value that is equivalent to, we have the temperature in degrees Celsius is equivalent to, we have 100 degrees Celsius plus 273.15. So we can have 1 Kelvin on top over 1 degrees Kelvin. If you want, you can just add direct without this if your lecturer is not strict. So we put the C here so that the C's can cancel there. So we have our 100 plus 273.15. This is going to give us a value of 373. So we have 373.15 degrees kelvins, like that. So with that said, we can now replace. So we know to say, let's move this a bit. So knowing to say, according to Charles' law, we have the volume number 1 over the temperature number 1 should be equal to volume number 2 over temperature number 2. So the volume number 1 is equivalent to, we have 117 milliliter over the temperature number 1 is equivalent to, we converted this to 373.15 kelvins should be equal to temperature number 2 or volume number 2 is, according to what we are given, it's 234. So we are going to write our 234 like that, 234 milliliter over our unknown temperature number 2, like that. All you have to do is cross multiply there so that this becomes equal to, we are going to have something like T2 times that, it will be 117 milliliter times our T2 should be equal to 373.15 kelvins. Then we have times our 234 milliliter like that over our 117 milliliter over our 117 milliliter like that. So our temperature number 2 will be equivalent to, if we press everything, we have 3 times 234. Then we divide this value divided by our 117. This is going to give us a temperature of 746.5. Remember, it will give you 0.3 kelvins. So the temperature will give you in kelvins, but they want what's temperature in degrees Celsius. So temperature in degrees Celsius. So this temperature in degrees Celsius, we know to say it's temperature in kelvins. Remember, you're moving from K to that, you have to subtract because of the alphabet. You can think of it like that. So we are going to subtract. By subtracting, we are going to have temperature in degrees Kelvin, which is our 476.3 degrees Kelvins minus our 273.15 degrees Kelvins. We can have the 1 degrees Celsius over 1 degrees Kelvin, like that. So we are going to have minus our 273.15. This is going to give us a value of 473.15 degrees Celsius. So this is the temperature required for that. Let's move on to our next question. B says, what is the volume occupied by this amount at the temperature of -25 and 752 milliliters of mercury? So to answer this question, if they have given you the volume, the temperature, and the pressure, just think of the ideal gas law. So we know that its PV should be equal to nRT. So dividing P to make the volume the subject of a formula, we are going to end up with V is equal to nRT over the pressure, like that. So our volume should be equal to, now the pressure, we are going to be using our R is equal to 0.08206. So our pressure has to be in ATM. So converting the pressure to ATM, we are going to get the value. So let's convert the pressure, convert the temperature, has to be in kelvins. So gases mostly is about converting. So let's begin with our temperature. So the temperature in degrees should be equal to temperature in kelvins plus 273.15. So let's just convert direct. So we are going to have our temperature in degrees Celsius, which is equal to, we have -25 degrees Celsius plus our 273.15, which is going to give us a -25 plus 273.15. This is going to give us a value of 248.15, like that. So this is the temperature in degrees kelvins, like that. So this is the temperature in kelvins. Then convert as well the temperature, the pressure to atmospheres. So if you have your 752 millimeters of Hg, so remember what you are going to do is you are going to put on top, you are going to put the one that you want to convert, which is the atmosphere. Down here, since there are millimeters of Hg, you are going to put them there, then put the values. In 1 atmosphere there is exactly 760, like that. So this and this cancels. So when you divide your 752 over your 760 times 1 ATM, you are going to get a value that is equivalent to, we have 752 divided by our 760. This is going to give us a value of 0.989 ATM. So with that said, we are going to say the volume, which is equal to nRT over the pressure. We are going to replace V is equal to, what is the number of moles? Wow, there was a lot of conversions here. So 20.2, we have to convert that to, so we have the number of moles is equal to the mass over the molar mass. So our mass is equal to 20.2 over the molar mass, which is NH3. We are going to have hydrogen, it's 1.01 times our 3, then we have our 14.01. So if we add 3 times this value, it will be equal to 3.03 plus our 14.01. When we add these, we are going to get our 3.03 plus our 14.01. This is going to be able to give us a 17.04 grams per mole. like that. So if that's the case, we are going to put it here 17.04 grams per mole. Then here on top we are going to have our grams like that. The number of moles will be equal to, we have our 20.2 divided by 17.04. When we do that, we are going to get a 1.1854 moles. So with these number of moles, we are going now to just replace, we are going to replace the volume is equal to nRT over our pressure. So the number of moles is 1.1885 moles times the gas constant, which is our 0.08206, times what is our temperature. So our temperature is equivalent to, what do we have, 248.15, if I'm not mistaken, 0.15 kelvins. So 0.15 degrees kelvins. Then we divide this over our other value, which is equivalent to the pressure. We found the pressure to be equal to 0.9, where is it, 0.989 atm, like that. So when we do that, the final answer, when we press everything, times 0.08206 times 248.15, then this value divided by 0.989, this is going to give us a 24.41. So this is the volume, which is in liter. So for this one, we have we have a 250 milliliter vessel, contains 1.02 grams sample of a gaseous compound and 25 degrees Celsius and 750 millimeters of mercury. What is the molar mass of the compound? So provided the mass, they want the molar mass. So what we are just going to do is, we are going to use the one that has already been made the subject of a formula. So just spell the word doctor with big letters. Doctor as a T should be equal to Mr. P, like that. So this is the formula we are going to use to find the molar mass, which is this one. So you can just change it to the molar mass like that. So now, so this will be over our pressure, so that will be our molar mass. So the molar mass is equal to density, like that, over the pressure, like that. So now let's just find the things. So density, we know that it's mass over our volume. So mass over volume is density. So density will be equal to our mass, according to what we have been given, is a 1.02 gram. So we are going to say 1.002 grams over the volume. The volume is equivalent to, we have a volume of 250 milliliters. So 250, then where there is the milli, you can put 250, not 550. We have 250. Milli is a unit of 10 to the power negative 3 liters, like that. Then we are going to calculate. So our density will be a 1.02 divided by a 250 times our 10 to the power of negative 3. So we are going to have something like the value, which is equal to a 4.08 grams per liter. So we have found our density. Then all we have to do is, let's convert the temperature to degrees to kelvins. So the temperature is given as 25 degrees Celsius. So let's convert it. So we have the temperature in Kelvin should be equal to temperature in degrees Celsius plus 273 point. We have 15 like that. So we are going to have 25 degrees Celsius plus 273.15. The temperature will be equivalent to, we are going to have our 25 plus 273.15. This is going to give us a 2 298.15 like that. So this is the temperature in kelvins, so we can put the temperature in kelvins like that. Pressure we convert from the unit of from milliliters, millimeters of Hg to atmosphere. So we have 750 millimeters of Hg. We multiply this by, we have since there is the millimeters of Hg down here, so that they can cancel. Up here we are going to have atmosphere. 1 atmosphere, there is 760 like that. This and this cancels. We are going to have our 750 divided by our 760. This is going to give us our 0.9868 atm. This will be our pressure in atm. So the pressure is 0.9868 atm. We have the temperature in kelvins is equal to 298.15. Then we also have the density is equal to 4.08 grams per liter. So we can, using our doctor, T should be equal to the Mr. P, like that. So we made it the subject of a formula. We have over P, so molar mass. So the molar mass should be equal to the density. We found it to be 4.08 grams per liter times R is equal to, our R is 0.08206. Then we have times, what is our temperature? Our temperature is equivalent to, we have the temperature is equivalent to 298.15 like that kelvins. Then we have over the pressure, which we found to be 0.9868 atm. So our molar mass, if we press everything, we are going to have 4.08 times 0.8206 times 298.15. Then we divide this value divided by our 0.9868. This is going to give us a 101.16 grams per mole. So that is what we have found. Looking at the next question we have, so answering this one, we have what is the pressure in atmospheres exerted by the mixture of 1 gram of hydrogen and 5 grams of helium when the mixture is confined in a volume at this temperature? What are the partial pressures and the of hydrogen and helium? Calculate the mole fraction and the mole fraction of hydrogen and helium gases. So 10 marks. So what we are going to do is that from here we are going to begin with the partial pressures. Use the partial pressures to add the pressure of the mixture. That means to say we have answered 2 parts, then answer this separate. So there are 2 ways of answering the first one, but let's just use Dalton's law of partial pressure. So before we do that, the first thing that you need to do is convert each and everything to the required units. So if you have the H2, so you have the mass of 1.0 grams, I can just say 1 gram of my H2. I need to convert this to the moles. Then I also have my 5 grams. I need to convert this to helium. I need to convert this to the required units. So for hydrogen, we have hydrogen gas. The molar mass will be 2 times 1.01, so it will be a 2.02. So we are going to have the number of moles is equal to the mass over the molar mass. So the number of moles is equal to what is our mass? Our physical mass in this case is equal to, we have 1 gram over the molar mass of hydrogen, which we have found to be 2.02 grams per mole. So if we divide this, we are going to have our 1 divided by 2.02. This is going to give us a 0.495 moles. So if we find the number of moles, we are going to find also the number of moles for this. It's 5 grams divided by, we have our 4 grams per mole. So the number of moles in this case will be equal to 1.25 moles of helium, like that. From here, we can just go direct to find the first part, which is calculate the pressure of the, exerted on that when the mixture is confined. So what is the pressure exerted by the mixture, meaning the two? So to find the pressure by the mixture, so we can say pressure by mixture, we can add the two pressures. It's either we can solve them separately or we can do this. Pressure by the mixture will be the number of moles, which is the total number of moles will be equal to 0.495 moles, like that. We add plus the 0. We have 1. We want the total number of moles because it's a mixture, 1.25 moles, which is going to give us this plus 1.25, which is going to give us a 1.745 moles. So this is the total number of moles. Therefore, if this is the total number of moles, we are going now to replace. So we have our N total like that. Therefore, the number of moles is equal to the mass over the molar mass. Oh, we have found the number of moles using the pressure, using the law, which is the ideal gas law, if we have been provided volume and all that. So using this, you can now calculate the total pressure using the total number of moles. Now, provided that the temperature is in degrees Celsius converted, so the temperature in kelvins should be equal to the temperature in degrees, which is 20 degrees, plus the 273.15. This is going to give us a 20 plus 273.15. This is going to give us something like a 293.15, like that. So this is the temperature in kelvins. Then just replace. So the total pressure will be equal to nRT, like that. So our number of moles is, the combined is 1.7. Where is it? We have 1.745 moles, 45 moles, times, what is my R? My R is equal to 0.08206. Let me move this. So we have times our temperature. So nRT, it is PV. So it's PV is equal to nRT. So we have to divide over V to make P the subject of a formula. Then the temperature, we have found it to be 293.15. We divide this by the volume, which is equivalent to, what's our volume? Our volume is equivalent to 5 liters. So we are going to divide the 5 liters like that. Then we are going to get a 1.745 times our 0.8206 times our 293.15. we are going to have a 419.775. We divide this over our 5. We are going to get a, sorry for that, the decimal point supposed to be here. Correct multiplication is cardinal. We divide by 5. This is going to give us 8.395, or should I say 6 atm. So this is the total pressure. So this is the total pressure of the mixture, like that. Then for the partial pressures, we are going to do the same. we are going to do the same. We have the partial pressure. According to Dalton's, it is the pressure of a gas in a container as if it is alone. So that's the partial pressure. So to begin with, let's begin with our hydrogen, which was the first thing mentioned. So the partial pressure of hydrogen will be equal to, not helium, of hydrogen will be equal to the number of moles of hydrogen. Then we have our RT like that, divided by the volume. Just the normal PV is equal to nRT, making V the subject of a formula. We divide by V like that. So nRT over our V. So this is the pressure of hydrogen. So the pressure of hydrogen will be equal to, what are the number of moles of hydrogen? So if you recall, the number of moles of hydrogen was found to be equal to 0.495. So we are going to say 0.495 moles. We multiply these moles by the R, which is 0.08206. Then we have times our temperature, which was found to be 293.15. We divide this over its volume. So the volume is equivalent to, as if it is the only gas. So you consider the whole volume, which was a 5 liters like that. So the pressure of hydrogen gas is equal to, we are going to multiply, so 0.4495 times 0.08206 times, we have our 293.15. Then this value we divide it by 5, we are going to get a 2.382. So this will be our pressure in atmospheres. Likewise, our pressure, our partial pressure, so we are partial pressure of helium will be equal to the number of moles of helium, RT over the volume like that. So as if it is alone, that is Dalton's law of partial pressure. So we have the number of moles in this case is equivalent to, we found the number of moles of helium, if you recall, it was a 1.25, which is this one. So we are going to put the 1.25 there. We are going to put a 1.25 there. So 1.25. Then we have times our R, which is 0.08206. Then we have times our temperature, which is equal to 293.15 kelvins, divided by the volume, which is our 5 liters. So we are going to have a 1.25 times 0.08206. Then we have times 293.15. This is going to give us a value divided by 5. This is going to give us 6.014 atmospheres. So this is the partial pressure. Remember, as if it is alone. You will find that if you add this and this, you are still going to get the total pressure. So if you were required to find the total pressure, you can also use this. You find the partial pressure of each, then add the two pressures. It is still going to give you the same 8 point something that we found. Then the last part of the question says, calculate the mole fraction of the gas. Calculate the mole fraction of the gas. So for mole fraction, we are going to say mole fraction. So the mole fraction of the gas, it will be equal to, it is a fraction, so therefore the mole fraction with the symbol X, it will be the mole fraction of let's say hydrogen, it will be equal to the number of moles of hydrogen over the total number of moles. So the number of moles of hydrogen was, if you recall, the number of moles of hydrogen was 0.495 moles over the total moles, which is our, when we added the moles, we had a 1.746. Then when we divide, we are going to get a 0.495 divided by a 1.746. This is going to give us a value that is equivalent to what do we have? 0.284 rounded off to 3 significant figures. So this is our mole fractions, our mole fraction of hydrogen. Likewise, the mole fraction of helium will be equal to the number of moles of helium over the total number of moles. So the number of moles of helium was found to be 1.25. We divide it by the total, which we found to be 1.746. So we have the moles. Remember, it does not have units. So we are going to have our 1.25 divided by 1.746. This is going to give us a 0.17 like that. So it's a fraction. That is what it's going to give us. Is there? Yes, we have done that question. So for E, it says that calculates the pressure exerted by 1 mole of ammonia in this amount of a vessel, assuming non-ideal behavior. So we are going to have our P plus our A, then we have our N over V, then we have squared. So this is the formula for the ideal gas equation. Then we have times our V minus our NB should be equal to nRT. So this is the equation. So we are going to now just divide. We want to make pressure the subject of a formula. So divide over N, divide this. You can even extend it to that. Then here we have N minus V minus NB. So this and this cancels. We are going to remain with our P plus our A. Then we have our N over V. Then we have squared should be equal to, we have our nRT over our V minus our NB, like that. We take this value this side, it will be pressure should be equal to our nRT over V minus NB. Then we have minus our A, N over V. Then we have squared, like that. So let's solve. We have calculated the pressure exerted by 1 mole of this in a 500 milliliter vessel at this temperature, assuming no ideal behavior, meaning we are looking at the real gas equation. So this is the equation, taking that. So this is the equation we are going to use. So our pressure, first let's convert the temperature. Temperature will be equal to, what do we have? We have we add temperature in degrees Celsius plus that temperature in degrees Celsius plus 273.15. So we have 25 degrees Celsius plus our 273.15. So when we add that, we are going to get so 273. Where 273 plus 25. This is going to give us, so we have 25 plus 273.15. So this is going to give us a 298.15, like that. So this is the temperature in degrees Kelvins. So therefore, after we do that, we are going to substitute. We have the pressure will be equal to, we have 1 mole, like that, times our R is equal to 8 point, our R is equal to, we have times 0.08206 times the temperature is 298.15. Then we divide over our 2, over our V minus NB, and we know that the what's this, the volume is 500 milliliters. So we can put 500 milli is 10 times to the power negative 3 liters minus what's our number of moles. So our number of moles is equal to, we have 1 times our B. So we have our NB. Our B is equal to 0.0371, 0.0371, like that. Then we subtract this minus our A, which is this part, A over N minus that. So let me reduce the font. So we have our minus, our A is, we have a 4.17, so we can replace it there, 4.17, like that. We multiply by the number of moles, it's 1 more, over, so we have our N over V. So we are going to write our V is 500 times 10 to the power negative 3 liters, like that. Then we square this. So we are going to have the pressure of, we have our 1 times 0.08206 times 298.15. Then we divide, we are going to have on top, we are going to have 24.47. We divided by 500 times 10 to the power of negative 3. This is going to give us a 0.5 minus 0.0371. Then we have minus, we have a 4.17 times 1 divided by our 500 times 10 to the power negative 3. That is going to give us a 2. So we get a 2 there, we square it. Final answer, pressure should be equal to 24.47 divided by our 0.5 minus 0.0371. This is going to give us a 52.86 minus, we have 4 times 4.17. This is going to give us a 16.68, like that. So this is going to give us, if we subtract our 52.86 minus our 16.68, this is going to give us a 36.18 atmospheres. So that is how we answer that. Thank you very much for watching. Hope you would like, subscribe and share for more. See you in the next tutorial.